It's an all-star session this morning. Our last speaker with us today is Jagoda Cupać. She's an assistant professor in structural design and building engineering group in TU Delft. Her research explores, just one more sentence, I'll give you a halfway one. Her research explores circular practices in the built environment, focusing on reusing glazing materials and redesigning components for adaptability. The floor is yours, Jagoda.
Thank you. Yes, thank you. I will talk today about an initiative, open data initiative, let's say, with a little bit of spice, with a little bit of results to give it context. Starting actually with a bit of personal reflection. It is something with working more and more on glass and glass reuse, that I notice in myself that I've developed a kind of empathy for glass. Because this is the reality today. We have very nice new projects, but a lot of our glass is locked into this kind of buildings, into residential buildings that urgently need refurbishment. And the glass from these buildings, well, risks being wasted, which when it goes like this, well, I feel it's a great pity to not use the potential of the glass we have because we are not organized well enough or don't know enough about it to still keep it in the loop. But what I also notice is that often this type of units are disposed with a kind of care. So I think I'm not the only one with this sense of empathy for the material and recognizing that it's not really ready to be wasted. So oftentimes, wherever I go, I see them disposed carefully on the side of the buildings, not in waste bins, as if to say, well, look, I'm still in one piece, maybe not good enough for this building anymore, but what else can be done with this piece of glass? So this is what my holiday pictures look like nowadays. And when it's a bigger scale project, I can imagine maybe there is a better future for glass to at least be recycled. But when I see just a couple of windows, I see a lack of infrastructure, though the understanding is there that this might still serve a purpose. So luckily, we see glass reuse happening already. So there is a recognition of the value of glass after its first life cycle. And there are some very nice examples of such reuse, as here the curved glass panels from the Caterpillar being used as internal partitioning walls in an office space. Or this example where the natural pavilion was designed to reuse, so according to the size of the source glass from a curtain wall panels in an office building in The Hague. I see also, at least in the Netherlands, that the reuse glass market is blooming, so there are more and more companies offering circular glass. There is infrastructure that can help scale this up. So we can automate this process, separation of IGUs and assembly of new IGUs. But as a structural engineer, I still remain with the question, what is the strength of this aged glass to be confident to reuse it? So in trying to answer this question, at TU Delft, we've been testing aged glass sampled from different projects, ranging from 15 years old to 55 years old glass. One of the projects is even on our campus. So here you see the process of glass being removed from the frame. It is cut out because there is asbestos contamination in the frame. It's a very old building. So this was the safest way to get it out. And then these are our bachelor students who did the testing and the cutting. So taking it to the lab, cutting into test samples. Then measuring the thickness at 4 points of each sample, and then performing ring-on-ring tests. which looks like this. And this should be a video, but it doesn't play. Well, it's a very short and straightforward test where glass is bent until it breaks. This is what results can look like. So not every sample we test is a valid sample for statistical analysis, but in bigger part they are. So we want to see the fracture origin within the loading ring. And what the results tell us. So here you see a variable plot of new glass, so here called as received glass, not aged, and a 25-year-old glass. So a shift to the left means the strength is lower as we would expect, and it's not dramatically lower, so that looks like good news. If we add to this 55-year-old glass, the strength is even lower, still makes sense. It is what we would expect to see. And the reduction you can see here, 10 and 40% in case of 25 and 50-year-old glass respectively. But then if we plot our 36-year-old samples, things get a bit more confusing. And you see that at low probabilities of failure, this glass even outperforms new glass. So for the characteristic strength, it is even 7% stronger than the new glass, though this is only one series of new glass, but still. And then if we add the 15-year-old, it crosses all of the other lines and has different relationships with differently aged glass, but it is not all that clear anymore. So this is an overview at different percentiles of differently aged glass, air, and thin side. Now, if you compare with the standards, what do we get? Here we consider different standards, K-mod that equals 1, and characteristic strength of new glass, which we know to be 45 megapascals. So depending on the standard, we get design values that range between 22 and 28 megapascals. So if we add this to our plot, things look quite okay. So most of the glass at low probabilities of failure falls within this range, though question is what is this 45 based on? So let's look into that as well. So these are plots according to the data from a report from association that we know today as Glass for Europe. They collected samples from 11 float lines. So there is altogether 742 samples tested, but these samples are much bigger than what we test. So that is a standard test for glass strength, 1 by 1 meter samples. If we test aged glass, this is not really something we can afford because we would, well, waste all glass on testing. But what we can see here is that thin side is not as strong as air side. This is common knowledge. And then the 45 is somewhere in between these two, okay? And in addition to the samples tested as received from different float lines, there was a series of artificially damaged glass, which then we assume served here as a safety margin to, let's say, this is a worst case scenario of a really damaged glass. This is how it will perform at low probabilities of failure. The strength will be 26 to 28 megapascals, and this gives us a safety factor with respect to 45 megapascals of 1.6 to 1.8. So this is our understanding how 45 megapascals has been agreed on. Still, these are values that come from very big panels. So the bigger the panel, the bigger the probability that there will be a critical flaw on it. So to compare our small samples, we would need to scale down our strength. So it's not looking that promising. Though looking at this approach to determine the strength, it seems we are all kind of uncomfortable with the very low tail of the variable distribution and don't think things are that bad, so maybe we can have a similar approach at some point for age class. Now, if we compare with other studies, we also run into problems because there are a lot of variations from study to study. Test methods, in general, coaxial double ring test, either according to the ASTM norm or the EN norm. None according to the norm based on which the 45 was established, so always small samples. Ring geometries vary widely, so even among these small samples, there are many different sizes of samples. Stress rates also vary a lot. Tests are mostly done at ambient conditions. And strength data is reported as a failure stress as recorded in the test, and sometimes it is expressed as time equivalent failure stress, which means there's not only failure stress reported, but also time to failure. So it is normalized to a certain time. And statistical analysis we see is, in general, two-parameter variable distribution. Parameters are determined in different ways, but never according to the EN approach that was used also in the 45 megapascal determination. We could perhaps recalculate if data was available to allow for comparison across different studies, but test data is mostly not available. So a very well-established solution for this is to share our data in a fair manner. So to make it findable, accessible, interoperable, and reusable, which in our field is not really common practice yet. So we're working on facilitating this the best we can. In the past, now almost 3 years, we have been working on Open Classroom. This is an educational community, so we've been creating open education platform on glass design and engineering, and the same can be applied to science, the way we do research. So we propose to have an open glass lab where we can exchange our results in a fair manner. So the first offering of the Open Glass Lab is this interactive strength analysis handbook. So what you can find here is a combination of a data repository. So there is a collection for data on the 40U research data repository, where you can share your data, and we will share ours. And then in this open interactive teach book, you can process statistically your data according to the methods that we have so far found to be most frequently used in studies. We're very open to add more, to adapt this teach book also, so it's as useful as it can be for everyone interested. And how it works, you open this in your browser. If you scan the code, you can do it right now. You select the number of data sets you want to plot. You enter your data, give name to your data sets, and then evaluate, and you get the results of the statistical analysis, including the variable plot. You can run all of this in your browser. Typically, the data we're handling is not so big that it would be really a problem to run in a browser. But you can also download it, the whole code, use it locally, adapt it as you like. Now, that would solve the problem of data not being available, but still, if we are all doing tests differently, it remains a challenge to make sense of the bigger data sets. So the ambition is to create large data sets that we can make meaningful conclusions from about the strength of aged glass. And one way would be to standardize how we test. Now, this is ambitious. So we decided to take a bottom-up approach and have a conversation. And the people you see here and on this slide, many of them I see in the audience, and they will be presenting or have already presented their work on this topic in these 2 days. We have started this conversation. It's work in progress. It is turned out to be more complicated than we thought to have an agreement, because we all have already test equipment and we have our reasons why we do things the way we do them, but we're coming to an agreement, I would say. So for annealed glass, for instance, we have agreed on the ring geometry of 40 millimeter load ring and 80 millimeter support ring, so to at least be looking at the same sizes of samples. For the stress rate, still a bit open. Some prefer to stick with 2. Some of us have been testing at higher rates. Though if we then normalize our strength data to a certain time equivalent, maybe we can bridge this gap also. And Open Glass Lab is there to support all involved in processing the data, so in doing statistical analysis in the same way. And I leave you with this open science image, which is a well-established movement, I would say. So I'd be very happy if we can bring it more into our field, collaborate, share our data transparently, which will increase the integrity of our research, making it available for everyone and hopefully result in an impact within our field, but also beyond. Thank you very much.